For the next talk, we're going to have Jordi Baylina, and he's going to be talking about major learnings building the zkEVM.
Hello, good afternoon, everybody. I am Jordi Baylina. I'm the technical lead at Polygon Hermes. Today I'm going to explain a little bit all the learnings and a little bit how we are building the zkEVM. My presentation is going to be a little bit technical. I'm going to try to go a little bit fast, but any questions you have at the end, you can ask to me or any of the team members that are right there. So feel free to ask and see how we are building that. Okay, so let's start. So mainly what we are building is a zkEVM. The EVM that we are building is, from the user perspective, it's quite easy to explain. The idea is that the user should be able to use any of the tooling of Ethereum. He could go to MetaMask and just do a transfer, can do maybe to remix and have a smart contract, compile and deploy a smart contract. So a normal user should not notice any difference by deploying to Ethereum, by programming to Ethereum, to deploying to layer 1. This is the goal, and this is what we are trying to achieve. The network, well, the system has like many pieces. You have the bridge, we have the smart contracts, the node. I'm going to focus very much in the prover, because the prover at the end is what distinguishes between a zkEVM and an optimistic rollup, and it's probably the most difficult part that we have to build. Okay? So what the prover have to do? Well, the prover starts from it's a circuit. It's a zero-knowledge circuit. It's a deterministic program. You want to see that. It takes the old state root. It takes some transactions. These transactions are normal Ethereum transactions, and I want to highlight that because these are transactions that are not signed differently or have different format. They are RLP, normal Ethereum transactions, generated with any tooling from Ethereum, and it computes a new state. And these transactions should be processed the same way that Ethereum processes transactions. If you are doing a transfer, you're doing a transfer. If you are deploying a smart contract, you are deploying a smart contract. If you are doing a call to a smart contract, it executes a call. And if this smart contract calls another smart contract, then this needs to happen. So it should work exactly the same way that Ethereum does. So how we build that? Okay, if we want to do it like in traditional zk systems, we have what we call the R1CS systems. Here, for example, we have our R1CS system. It's just this is very much like writing, like doing an electronic circuit with gates that do a computation. But it's a gates that they don't feedback. They just you put some inputs. With these gates, you compute a deterministic program, and at the end, you have the solution. As you can imagine, this is quite hard, quite expensive. You need thousands of millions of gates if you want to do a zkEVM, and this is not practical on that. So, well, we had to invent an equivalent to the equivalency to the hardware. We need to invent what we call it the clock. Okay, so the clock. The idea is that we have a smaller circuit, and the idea is that we execute this circuit many times. Okay, this is what's this is what we call with this polynomial identity language, because instead of having signals, we have like an array of signals. An array of signals, we can represent that with a polynomial. Okay, and the idea is that we have state transitions. So we can, from each part of the polynomial, so it's from one state to the next state, we have some gates or some constraints, and then the idea is that we have state machines. And if we have state machines, then we can build processors. And once we have processors, we can create an assembly. And what we do is we program, so we created a processor with this arithmetization, with this system that's executing an assembly code, and this assembly code is mainly an interpreter of an Ethereum state machine. This is the idea of how we are building this. Okay? So we have like these two big pieces. One is the arithmetization, which is a quite a small circuits, and then we have the assembly. Okay? So let's see how we are. I want to explain here, give a big highlight on how we are doing this arithmetization so that the people we understand how it works. To understand this, the idea of this state machine, I'm going to show what would be the hello world of PIL, this language that we created in order to create this arithmetization, or this hardware if you want to be this equivalence. Okay? So here we have well, we want the problem. We can set up this problem. This is a hello world problem. The idea is that we work in a specific field, and then we have a number, and then we want to find two numbers that when we apply a Fibonacci series 1045 times, then it gives that number, so that you know these two initial numbers, A0 and A1, that applies to this. We can do that in circum easily. This would be just a loop in a normal circum, but we want to use PIL. So in order to use PIL, we need to define state and a transition state. In this case, the state is the last value and the before last value. And then we define this state transition function. So how we are, what are the next value of these registers? Okay, so in this case, we said, well, that the before last value is going to be the last value, and the last value is going to be the addition of the last values. So we have this state. This is very important because this is a state machine. Okay, and again, if we have a state machine, we can build the processors. We will see it later. Okay, so we have this set of values that are the values that these registers happens in every place. This we call it the trace. Okay, and we can represent that with a polynomial. A polynomial at the end is, as I explained, is simply a set of values. It's actually area evaluations to different points. And then we have these polynomials, and we define these state transitions. So how we write that in PIL? Okay, well, if we write that in PIL, the idea would be this. We would define the before last and the last, and then we would define this state transition. In this case, would be the before last minus last equals 0. Okay? And then the last is equals to the before last plus last. So the prime means the next one, and here we say that the next one is this one. The problem here, we add this is last at the beginning, because the problem is that this state transition function needs to fulfill in all the places, and including the last one with the first one, because this is a rotation, so it gives all the way around. So in this case, we add here what we call it a constant polynomial, so a fixed polynomial that's exactly the same. That's just it's 0 to all the points except the one that's 1. This is fixed. It's part of the verifier, if you want. It's a pre-computed polynomial, and then we just add this constraint. Okay, so we say if its last is 1, this is 0. That means that whatever value you put at the end is going to fit with the first one. Okay, and then we also define a public input. In this case, would be the output. This is what we will be sharing the circuit. And then we define that the condition for the public output. Okay, so this is how the idea of how it would work a single state machine. This polynomial, well, of course, if we want to write the full circuit, we need to compute the pre-computed polynomials, and we need to compute the trace. We need to actually execute. In this case, would be, for example, we have 2 inputs, and then we evaluate these polynomials at all the points. So we build all the trace. So once we have these polynomials and we have this PIL with these identities that needs to fulfill, then we are done. With this, we have a tooling, we call it PIL Stark, that we automatically can create a proving system, a Stark proving system for generating a proof and a verifier. Okay, so this polynomial identity language is it's more it's more powerful than that. For example, it can do permutation checks, not only check state transitions, but for example, we can say that one polynomial is a permutation of another polynomial, so that the values in one polynomial are the values of the other polynomial. We can also do permutation checks in multiple rows and with a selector, so that you have like maybe these 2 columns. This needs to be equal to these 2 columns, no matter the order, but only in some specific lines. So we can do that. And we can also do lookups. Okay? So lookup is just an inclusion, so that all the numbers in the first polynomial must be included in the numbers of the second polynomial. And of course, we can do that also in a multi-row and with a selector. So all the numbers of the selected 2 columns must be included in the last one. Okay? So this allows us a lot of flexibility. We have also the idea of copy constraints. The idea is that we can have a polynomial, and the idea is that we want to be sure that, for example, the first evaluation, the third, the fourth, and the fifth are the same. So we define this with a constant polynomial that's just a permutation of the identity polynomial, of the x polynomial, with rotations with all the values that needs to be copied or that needs to be the same. Okay? And of course, we can do that in multi-value. So with this, we have actually we have Plonk. Okay? So with this, this is, for example, this is the Plonk paper. Here we can define, this is an example of Plonk. People that is familiar with Plonk, they will recognize these polynomials, and this is the conditions of Plonk. But this is, as you can see, this allows us to extend much more than Plonk, because this allows us to define custom gates, to define different permutations, have different state machines that are computing different parts and connect them together. Okay? Actually, we combine that also with zkEVM. With zkEVM, we added the concept of custom templates or custom gates. And the idea is that you can combine Plonk and zkEVM. So there are pieces that you want to have state machines, like more for like processor likes, and others that are circuits. For example, Ketchup is very much a circuit, and it works better with circuit language. So we can combine both things and call one from the other and the other of one. So we have the best of both worlds here. So this is all the tooling that we build. We used to build the zkEVM. Okay? So we have this tooling, which is Stark, that actually, once you have these polynomials constraints, so we have all these polynomials that need to fulfill these specific identities, we can generate Stark. And not only that we also generate, this tool also generates all the recursion. So it generates a Stark that verifies the Stark, and you can aggregate them, and all this is quite automatic with this tooling. By the way, this tooling is absolutely open source. Anybody can use it, and it's available for the people. Okay? And the other thing that also includes this tooling is that you can also verify this Stark with Plonk or Glo16. So with a normal circuit, that then you can use Snark.js or Rapid Snark to prove the last one. So we don't have this, for example, we can verify a Stark, fast Stark, with just with the gas cost of a normal Glo16 in the last part. Okay, but let's go back to the prover. Okay, so let's go back to how we build the circuit. Okay, so well, in order to build the circuit, we need to build a processor. Okay, so processor is a state machine. We have some registers, we have some operations, and then the status of the next registers depends on the operations that we are having. Okay, so in this case, we have the operation. The operation is a set of polynomials. We could pack that with a single number. You know, we can have a polynomial with the values, and each one is an instruction. But actually, we have like many polynomials, and each one is part of the instruction. Okay? As part of the instruction, we have, for example, in A, in B, in C, in D, in E, set A, set B, set C, set D, and set E. Okay? So here is how we define the next step. We create an intermediate value here. The intermediate value is, if in A is 1, it's going to be A. If in A is B, it's going to be B, and the others are 0. So you can have a selector. You can add them. Also, you can add A and B. Or okay. And then it is the operator, and then we assign a prime. If it's set A is 1, then we are assigning this value to A. And if not, we just keep the last value. Okay. So, for example, for doing a move between register A and register C, in A would be 1, C would be 1, other registers would be 0, and then this equation would hold. Okay. We have also as part of the instruction, we have like a constant value. This is very much for immediate instructions when you want to just assign a specific value to a register. And then we have also a special polynomial. We call it freeing, and this is for deterministic. And a lot of times it's very useful. For example, you want to do a division. Division is quite complex. So the idea is that you put the result of them. So you put the result of the division, and then you check the multiplication. You just the division by times the quotient and the multiplication. So some instructions allows you to put some value. Of course, you need to be very aware that when you're putting some value, then you need to check after. Okay. As a normal processor, we have a program counter. A program counter is, it's a register that tells you exactly which line of code you are executing from the ROM in this case. Okay, and we have also conditional instructions. So it says if this value is this, then you go jump to this other place. So we have a full assembly in that part. Okay, for that we need to check some comparison and then just assign this new program counter. Okay. With this, of course, here with this we can. This is a processor. We can put an instruction. So here we are not forcing to execute a specific ROM. So how this will execute this would be a processor that would execute, but you would be able to execute an instruction. So how we force that the instructions that are executing are not random and are the specifics that are in the ROM. Well, the way that we are doing is quite easy. We have all the instructions, which is all the polynomials that represents the instruction. In this case, would be an 8. Okay, and here we have the program counter. Okay, and this needs to be included in the ROM. The ROM is, well, it's just the numeration. This is just the line number of the ROM. So the first instruction is A, jump, and then the line number must match with the program counter. So that means that because there is only one line 2 in the ROM, if I have to execute the line 2, then this must be so this instruction must be the one that's in the ROM. Okay, so this is the way that we are forcing to execute a specific ROM. Okay, we have also a memory. A memory is a normal read-write memory. You can read and write. The trick here is we sort. So we sort all the access to the memory, all the reads, writes, but we sort them by addresses. So we have like another state machine where we do all the reads and all the writes, order it in the same, but so we sort first by address and then by the program, the counter, the program, so the line, so the execution trace number that we're executing. That means that all the reads in this case, for example, all the reads and writes of the position 3 are done here, and then these are done with a single register. So we have a register which it's temporarily using as a register 3. And then we connect both state machines with a permutation check. So all the instructions that we're executing here must be included in there. Okay? Of course, here we need to do a check to be that this table must be sorted the right way, but this is the way we implement RAM. Okay? We have other state machines like arithmetic state machine, which does, for example, some 256 bits operation in there. So this is a state machine that's specific to doing 256 bits operation. And then here we have via a lookup or a permutation check, when we check that the instructions that we are using, that we are executing in the main processor are also that we are assuming here that this multiplication is right, but we are also verifying here. So we need to guarantee that this operation is validated in the other state machine. So here are some of the tricks that we learned during the implementation, during the execution, during this year on the creation of this state of the zkEVM. Okay, the big picture of the circuit. Of course, we have the processor, we have the RAM, we already talked, we have the ROM, which is, we already talked a little bit. We have a storage, okay? So for the storage, we are using a sparse Merkle tree, with some slightly modifications with the Goldilocks, so that works that way. It's not Patricia tree, but it's a specific Merkle tree that's very optimal, with a hash function that's very optimal to work in this prime number, and it's a specific. And the storage itself is even another processor, because for the sparse Merkle tree, there is a lot of logic there. So it's a kind of so it's another subprocessor that's computing the reads and the writes, and then with lookup, we connect it to the processor. Okay. We have also the binary. In the binary here, we do all the instructions, all the 256 instructions for add, sub, less than, equal, signs, and XOR, and so on. We have also the arithmetic state machine, and then we have the ketchup. Okay, for the ketchup, actually, it's a circuit, but here the trick here is that we are doing, it's a circuit that's doing like many many cake checks at the same time because each one is using a different bit, and via lookup we do the gates, mainly our XORs and so on. Here, probably one of the most difficult state machines here is the padding one, because the cake check we need to pad that, and then it's for doing all the padding we need to deploy that, and this is a kind of a ROM, and then we check on that, but that's a thing on there. Okay. So this is very much the hardware. We call it hardware. It's not hardware. Here is polynomials, but actually this arithmetization, we like to call it hardware because this is the low level. This is where the things, the metal on there. Okay. So on top of that, of course, we have an assembly. This is a processor. We have an assembly, and then in the assembly we need to implement the Ethereum. We need to implement all the logic that Ethereum happen. Okay. And I want to show you here some of the opcode, how it looks like a little bit. Okay. This is this is a part that where we are processing all the opcodes. Here we have the add, the mul, subtraction, okay, division, so on. But maybe we can go at the end, maybe where there are some more interesting ones. Let's see here at the end. Well, jump destination. Here we have, let's see the loops right there. Well, here is a lot of code right here. Yes, the return. Here we have returns. We have here we should have delegate call. Here we have create to. So here we have all the opcodes of Ethereum. So that's why we are so much compatible, because we are programming Ethereum exactly the same way that Ethereum does. Okay. Maybe another piece is the RP processing. When we get a transaction, we need to process. So we need to parse in RP and all the fields and do all the logic that actually Ethereum has. Okay. So this is some example of the code. Everything is available. It's in open source, so you can take a look at the repo and check how everything is done here. So yeah, let me just. Of course, then with this we have the ROM. After the ROM, we need to create a proof. Here we have this recursion. The recursion stacks is very useful mainly for two things. One, it allows us to aggregate many proofs in a single proof. So this is one thing. And the other is also that the proof is, you can pack the proof. The proof can get, every time that you recurse one time, it's getting smaller. So both things combined together just to have the last growth 16 proof. Okay. As I mentioned before with the ROM, so we are very much Ethereum. Actually, we are running all the Ethereum testnets. We're using all the Ethereum suite for testing the compatibility. This is the roadmap. Right now, more than 85% of the tests are passing. Of course, getting to the idea is to get to be at 100%. Well, as you get closer to 100%, it's more difficult. But yeah, that's the idea. We are testing all the edge cases and all the, just underflows, overflows. You can imagine all the testing that's in there. And this is, well, for us, this is important because this gives us good compatibility, and from the end user, should not notice the difference of programming in Ethereum and programming here. Okay. Here, I want to talk also a little bit about benchmarks. Here is, well, there is a little bit modification here from when I explained these numbers in Paris. Actually, the proof time right now, that the current proof that we are working, and this is a work in progress, but the current proof that we have at this point it takes about 15 minutes in a quite big 64-cores GPU. But the good thing is that it can process, let's say, 1.5 megabytes. This is probably short. It's much more than that, but we are finishing to do the numbers. So that means that, and this is the important part, is that the cost per transaction is going to be a sub-cent of dollar cost of transaction at this point. And we still have a lot of margin to improve. Actually, we are working really hard with GPUs and FPGAs, and there are a lot of optimizations that are in the to-do list that probably will get these times down. Okay. Roadmap, well, at this point we open sourced that 2 months ago. We are working really hard right now in bug fixing and stabilizing the different pieces of the piece. Currently, the internal testnet is working quite well. And yeah, we hope that very soon we can publish the public testnet with everything in there. And then we are already started to organize the audit here. We're having a lot of help, for example, from the Ethereum Foundation, and from even we are collaborating with other teams here because auditing these systems is not easy. There are a lot of new code and a lot of new things to check and to double check, and this is going to be a little bit challenging, but we are ready. We are ready to start this process, and the idea is to, let's see. This is just, of course, this is not a commitment. We are not going to launch anything until it's safe and it's audited and we have enough warranties. So 0%, so 100% warranty is that's no bugs. We will never have, but we don't want to be crazy, and we want to launch the things as safe as possible. So we need a lot of people to review, a lot of people to check, and to be sure that what we are launching. Let's see if we can launch that by the end of the year, beginning of next year. That's our hope. Okay. So that's very much it. But just before ending, just that everything is open source. If anybody is interested to take a look, to check, or even to using all the tooling that we built for even building other applications is available there, please contact us. Here we are open in Polygon. We are very open to the community and to talk with any people that wants to use this tooling. And that's very much. Thank you very much. I don't know how much time.
So thank you very much, Jordi.
No questions?
Unfortunately, we don't have time for that,
okay,
but everyone can catch up with him later, and also the slides and the video will be available. And again, thank you. Another round of applause, please.